Hello students, welcome to today's lecture on theory of machines. This is the part 2 of the lecture on band and block brake. In the part 1 of the lecture, we discussed the construction and working of the band and block brake. We then tried to understand that why the tensions in the band and block brake are taken as T0 and Tn on the slack side and the tight side respectively. We also saw how the tensions act between the two blocks in the band and block brake with N blocks. We then derived the equations for the ratio of tensions Tn upon T0 and also for the braking torque in case of band and block brake. We further discussed that the force P applied at the end of the lever can be found out by using the same method which we learned in the differential band brake, that is by considering the free body diagram of the lever and taking the moments of the forces acting on the lever about the fulcrum. In today's lecture, we will solve some numerical problems based on the band and block brake and see how to take the moment about the fulcrum to find the force applied P. So let's proceed with the first problem. The problem statement is as follows. The maximum braking torque acting on a band and block brake as shown in figure is 2000 Newton meter. The band is lined with 15 blocks, each of which subtends an angle of 12 degrees at the center of the rotating drum. The coefficient of friction between the band and the block is 0.3. The diameter of the drum is 680 millimeters, whereas the thickness of the blocks is 60 millimeters. Find the least force required at the end of the lever, which is 480 millimeter long. So this is the configuration of the band and block brake given. It is having 15 blocks. The distance of the end A from the fulcrum is 125 mm and the distance of the end B from the fulcrum is 25 mm. The length of the lever is 480 mm. The distance at which the force P is applied from the fulcrum is 480 mm. Now let's proceed with the solution and see what is given. So the given parameters are: diameter of the drum is 680 millimeter, that is 0.68 meter. Therefore the radius of the drum will be 0.34 meter. Thickness of the block T is equal to 0.06 meter. Angle of contact 2 theta is 12 degrees. Braking torque is given as 2000 Newton meter. The length L is given as 0.48 meter. Friction coefficient mu is 0.3. Distance A is taken as 0.125 meter and B as 0.025 meter. And the number of blocks are 15. And we have to find the least force P. Now as the distance A is greater than B, hence the force P must be applied at C downward. And the force P will be least if the end of the band attached to A is slack and the end attached to B is tight. This is only possible if the drum rotates in the clockwise direction as shown here. Moving ahead, the ratio of tensions for the band and block brake with N blocks will be Tn upon T0 is equal to 1 plus mu tan theta divided by 1 minus mu tan theta whole to the power of N. Substituting the values of mu, theta and N, we have Tn upon T0 will be equal to 1 plus 0.3 into tan 6 degrees divided by 1 minus 0.3 into tan 6 degrees whole to the power of 15. From here we get Tn upon T0 is equal to 1.065 to the power of 15, which is equal to 2.573. This gives us Tn is equal to 2.573 times of T0. Further, braking torque is given by Tb is equal to Tn minus T0 into R, where R is equal to Rd plus T. That is, R is equal to 0.34. Our radius of drum is given as 0.34 plus the thickness of the block is given as 0.06 meters. So R will be equal to 0.4 meters. Now substituting the values of braking torque and radius of the band, we have Tb is equal to 2.573 T0 minus T0 into 0.4. Tn is kept from this equation. This will give us Tb is equal to 1.573 T0 into 0.4, and now substituting the value of Tb, we have 2000 is equal to 1.573 T0 into 0.4. This will give us T0 is equal to 3178.6 Newton. Now substituting the value of T0 in this equation, we will get the value of Tn as equal to 2.573 into 3178.6. Therefore, Tn will be equal to 8178.5 Newton. Now, having calculated Tn and T0, we need to find out the least force P. So, as discussed in the previous lecture, that the force P can be found out by considering the free body diagram of the lever and taking the moments of the forces acting on the lever about the fulcrum point. So let's see the free body diagram of the lever. This is the free body diagram for the given configuration of the band and block brake with drum rotating in the clockwise direction. As the drum is rotating in the clockwise direction, forces acting on the brake lever are P, T0 and Tn. Moment of the tension T0 about the fulcrum point will be a positive moment as it will be rotating the lever in the anti-clockwise direction, and the magnitude of the moment of T0 will be T0 into the perpendicular distance of the line of action of the tension T0 from the fulcrum, that is nothing but 125 millimeter. Now force P will be rotating the lever in the clockwise direction, so the moment will be negative and the magnitude will be P into the perpendicular distance of force P from the fulcrum point, that is 480 millimeters. Similarly, Tn will also be rotating the lever in the clockwise direction about the fulcrum, so the moment of Tn will be negative and the magnitude will be Tn into the distance 25 millimeters. So taking moment of all the forces on the brake lever about the fulcrum, we get T0 into 0.125 minus P into 0.48 minus Tn into 0.025 is equal to 0, where T0 is having the positive moment and P and Tn are having the negative moment. Now this equation can be rewritten as P is equal to T0 into 0.125 minus Tn into 0.025 divided by 0.48. Now substituting the values of T0 and Tn, we have P is equal to 3178.6 into 0.125 minus 8178.5 multiplied by 0.025 divided by 0.48. This will give us the value of P, the force applied, as 401.8 newtons. So this is the least force P that is to be applied on the lever. So this is how you can use the method of taking moments about the fulcrum point to find out the force P to be applied on the lever. Now let's move towards the second problem. The problem statement is like this. A band and block brake having 12 blocks, each of which subtends an angle of 16 degrees at the center, is applied to a rotating drum with diameter 600 mm. The thickness of the blocks is 75 mm. The drum and flywheel mounted on the same shaft has a mass of 1800 kg and have a combined radius of gyration of 600 mm. The two ends of the band are attached to pins on the opposite sides of the brake fulcrum at distances of 40 mm and 150 mm from it. If the force of 250 Newton is applied on the lever at a distance of 900 mm from the fulcrum, find the maximum braking torque. Second, the angular retardation of the drum. And third, the time taken by the system to be stationary from the rated speed of 300 rpm. Take the coefficient of friction between the blocks and the drum as 0.3. So let's see what will be the solution of this problem. So this will be how the band and block brake will be looking like. It has 12 blocks. The distance from the end A to the fulcrum is A, and the distance from the end B to the fulcrum is B, and the distance of the point at which the force P is applied from the fulcrum is L. Now let's see what is given to us. Diameter of the drum is 600 mm, that is 0.6 meter. So the radius of the drum will be 0.3 meters. The thickness of the block T is equal to 0.075 meter. Angle of contact to theta is equal to 16 degrees. Least force that is applied is P is equal to 250 Newton. Length L is equal to 0.9 meters. Friction coefficient is 0.3. Distance A is 0.15 meter. Distance B is 0.04 meter. Number of blocks N is equal to 12. Mass M is equal to 1800 kg. Radius of gyration K is equal to 600 mm. And speed N is equal to 300 rpm. So the ratio of tensions for the band and block brake with N blocks is given by Tn upon T0 is equal to 1 plus mu tan theta divided by 1 minus mu tan theta to the power of N. Substituting the values, we have Tn upon T0 will be equal to 1 plus 0.3 into 10 8 degrees divided by 1 minus 0.3 into 10 8 degrees whole to the power of 12. This will give us Tn upon T0 is equal to 2.752. That means Tn is equal to 2.752 times T0. Now, as we are given the least force applied P is equal to 250 newtons. So, let's see the free body diagram of the bend and block brake in the given configuration. So, this is the free body diagram of the lever in the given configuration and the clockwise rotation of the drum. Force P is applied in the downward direction and tension T0 at the end A and tension Tn at the end B. We have assumed that A is equal to 150 mm and B is equal to 40 mm. As A is greater than B, P must be acting downwards, and for the maximum braking torque, the rotation of the drum should be in the clockwise direction. Now, taking moments about the fulcrum. Again, the tension T0 will be rotating the lever in the anti-clockwise direction, so it will have a positive moment, and the magnitude will be T0 into the distance A from the fulcrum. Further, the force P will be rotating the lever in the clockwise direction, so the moment will be negative and the magnitude will be P into the distance L from the fulcrum. Similarly, Tn will be also rotating the lever in the clockwise direction, so again the moment of the Tn will be negative and the magnitude will be Tn into the distance B. So writing the moment equation, we have T0 into A minus P into L minus Tn into B is equal to 0. T0 has positive moment and P, L, Tn are having negative moment. Now substituting the values, we have T0 into A is 0.15 meter minus P is given as 250 Newton and L is 0.9 meter minus Tn, that is kept from this equation. Tn is equal to 2.752 T0. So minus 2.752 T0 into B is 0.04 meters. From here we will get T0 as 5636 Newton. Substituting this value of T0 in this equation, we can get Tn as 5636 into 2.752. This will give us Tn as 15511 newtons. Now, having calculated the values of T0 and Tn, we can calculate the braking torque as Tb is equal to Tn minus T0 into R, where R is the effective radius of the bend and is given as R is equal to Rd plus T. That is, R is equal to Rd is given as 0.3 and thickness of the block is given at 0.075. Therefore, R is equal to 0.375 meters. Substituting the values of Tn, T0 and R in the equation of braking torque, we have Tb is equal to 15511 minus 5636 multiplied by 0.375, which gives us the braking torque as 3703 Newton. So this is the braking torque on the bend and block brake drum for the given configuration. Now further, we need to calculate the angular retardation, as we know that the braking torque is given as Tb is equal to I into alpha, where I is the moment of inertia and alpha is the angular retardation, and this is equal to mk square into alpha, as moment of inertia is equal to mass into square of the radius of gyration. Substituting the values of Tb, m and k, we have 3703 will be equal to 1800 into 0.6 square into alpha. This will give us alpha as equal to 5.71 radian per second square. So the angular retardation of the drum will be 5.71 radian per second square. Further, we need to calculate the time taken by the system to be stationary. So for this, we have initial angular speed as omega 0, which is given by 2 pi n by 60. Substituting the value of n, we have omega is equal to 2 pi into 300 divided by 60. This gives us the initial angular speed omega 0 as 31.4 radian per second. Now, as the drum has to be stationary, so the final angular speed omega will be equal to 0. And we know that omega is equal to omega 0 minus alpha t. Substituting the value of omega 0 and alpha, we have 0 is equal to 3.14 minus 5.71 into t, and this gives us t is equal to 5.5 seconds. So the time taken by the system to be stationary is 5.5 seconds. So these are the two numericals which we have solved, in which you have learned to calculate the least force that should be applied on the lever, and also how to calculate the braking torque, the angular retardation, and the time taken by the system to be stationary. So I hope you have understood how to make the various calculations in case of bend and block brake, and I wish you so do practice some more problems from your textbook, and in case of any doubt, please feel free to contact me. Thank you.